In the last video I looked at a computer-intensive method called permutation tests, and in this video I'm going to look at a different type of computer-intensive method called simulation. And the example I'm going to look at is kind of interesting. Let me show you a histogram. So this is a stage performer who picks a volunteer in the audience to think of a number, a two-digit number between 10 and 99. And so you would think, and then the idea is the stage performer is going to try and guess the number. So you might think that if someone's picking a number at random, if I was to look at a histogram, then we ought to see a fairly even distribution here, but it's clearly not very even. So kind of interesting. And so I guess this is how stage performers that use this trick take advantage of this tendency for certain numbers to be more commonly picked than other numbers. And so the test that we're going to do here is we're going to do a hypothesis test where the null hypothesis is that two-digit numbers are chosen with equal probability, and the alternative hypothesis is that two-digit numbers are not chosen with equal probability. And we're going to use simulation to do that hypothesis test. So this kind of scenario kind of lends itself to a scenario we looked at earlier in an earlier video where we used a chi-squared test. And so if I just set up the chi-squared test here, then I get a chi-squared test statistic of 1,231. So I'm not going to spend too much time going through this code here, because this is something that we did before. I'm just going to focus on the result here, which is we get a chi-squared test statistic of 1,231. But remember, there's usually assumptions underlying most parametric tests, and for the chi-squared test, the chi-squared goodness of fit test, one of those assumptions is that we can have no more than 20% of the categories having expected values less than 5. In this case, it turns out that for every single category represented by the bars here, the expected frequency is 3.5. So they're all less than 5. So if we were to try and run the chi-squared test on this data, that assumption doesn't even remotely pass. And so we could run the chi-squared test here, but the results would be meaningless. So we need to come up with an alternative way of finding the null distribution for this test statistic that we've just calculated. So we're going to use simulation to do that. So the way that simulation works is, let me just show you an example. So I'm just going to isolate this bit of code and run it, and let's look at what I came up with. So this is a simulation the same size as the data, so 315 observations, and these are numbers that are sampled from between 10 and 99, so two-digit numbers between 10 and 99, and I'm using the sample function with replace equals true. So if you recall, in the last video we used this sample function, but we had replace equals false because we were sampling without replacement, because we wanted to create a permutation. But that's not what we're doing here. Instead, think of it this way. We're picking the first number, 62, randomly from between 10 and 99. And then the second number, I want to allow the possibility of picking 62 again. And so I'm going to replace it in my sample and pick the second number. The second number I didn't get 62 again. I got 47. And then I'm going to put the 47 back into the sample and pick the third number. So I'm replacing every time. So I'm sampling with replacement. And so you'll see, let's see if I can eyeball a repeat. Might be a little difficult because it's like a swarm of numbers in front of me that I'm looking at now. You've probably located a repeat already, but I'm struggling. There we go, there's 2 in a row. Okay, so here I got a 66 for this number, and then I put the 66 back in the sample, and I picked another number at random, and I got 66 again. So that's different from a permutation. A permutation, you don't get any repeats, but this sampling with replacement, I do get repeats. So what I'm doing here is I'm sampling these numbers at random. So I'm sampling as if the null hypothesis was true, that 2-digit numbers are chosen with equal probability. That's what this bit of code is doing. And so that's going to allow me to calculate a null distribution, and I'll be able to figure out a p-value. So let's go through this now. So I've done the first 2 steps of the hypothesis test. I've stated my hypotheses and I've figured out my test statistic, and now I'm going to set the number of simulations at 10,000. I'm going to set an empty vector to store the results, and then I'm going to run through this loop so that I create a null sample and figure out the chi-squared test statistic for each of those samples and store the results, and then I'll just keep track of the simulations. So let me do that, and this one runs a little quicker than the permutation example. So it's done already. Like, that took what, 3 seconds? And so now the rest is the same as it was in the previous video. So here's my histogram. My observed test statistic, it's not even on here. It's, what was it, 1,231, I think? Yeah, 1,231. It's like way out in the tail. So I don't even really need to do this calculation. I'll do it anyway, but it's going to be 0. So that's my p-value. I'm so far out in the tail, it appears very unlikely that that test statistic could have come from this null distribution. So that's step 3. Step 4, make a decision, draw a conclusion. Because this p-value is smaller than 0.05, my significance level, I reject my null hypothesis in favor of the alternative hypothesis and conclude that the two-digit numbers are not chosen with equal probability by audience members who are being asked by the stage performer to pick a number at random between 10 and 99. There's certain numbers that they tend to favor. Turns out that there's actually a built-in method in this chi-squared.test function. There's this argument here, simulate.p.value, which you can set to true, and it'll actually do this simulation for you, which is kind of neat. So you don't need all this code for this particular example. So it's giving us our test statistic here, and then it's giving us our p-value, and yeah, really essentially 0, just the same as we got. So again, just as with permutation tests, simulation is a very general technique. It can be used for lots of different types of examples, not just this chi-squared example that we've done here. Any example that you can think of, pretty much, you can analyze using simulation. All you have to do is figure out how to create the null distribution for the test statistic. And in lots of examples that's fairly straightforward. In some examples that's not straightforward. But when it is, this is a good computer intensive technique that you can use. Okay, so in the next video we'll look at another computer intensive method called bootstrapping.